All right, so homework 2, problem 2, it's about oxidation. So petroleum hydrocarbon can be oxidized by microorganisms in biofiltration soil in the presence of oxygen as electron acceptor. A typical redox equation of a hypothetical organic chemicals is the following. So we have our hydrocarbon here. We have oxygen on one side, and we have, as products, we have CO2 and water. So part A is to calculate the oxidation state of all elements and identify which elements being oxidized or reduced. B is to write the oxidation reaction, C, reduction reaction, D, write balanced redox reaction, which is basically whenever we do the summation between B and C here, and then write possible design modifications to increase degradation of this system. Okay, so let me share the whiteboard. All right, so let's write up here. Homework 2, Q2. So it gives the equation of this petroleum hydrocarbon being oxidized, which is C6H6O plus O2. And then we have CO2 and water. Okay. So first question is to calculate the oxidation state of all elements in the equation. All right, so let's start with, I'm gonna put this in blue, with oxygen, because it's a single element in here, or a single molecule. So we know that the oxidation state is 0 there. But we also know that if oxygen is with other molecules in a, or with other atoms in a molecule, we know that the oxidation state is -2, right? So we know that this oxygen here is -2. This one is 0. We know that the hydrogen here is +1. So by calculating that, we know we can calculate the oxidation state of this carbon here. So we have -2 plus 6, because we have 6 hydrogen. So -2 plus 6, it should be equal to, because the whole molecule needs to be 0. So 6 times x. Okay, so we have plus 4 equals to 6 times 6x. Oops. So we know that x equals to 4, 6, and make sure that this is right. -2. So it should be minus 4, 6, right? Let me see. Yeah, it should be minus 4, 6 in here. Because if I add, so minus 4, 6 times 6, I have -4. And then with the oxygen, I have -2. And the hydrogen gives me -6. So if I add this all up, it's going to be 0, which is our charge of the molecule. Okay. So this is -6. Oops. Well, let me rewrite this part in here. So we know that -2, which is the oxygen, plus 6, which is 6 times 1 of the hydrogen, plus 6x equals to 0. Okay. So we know that it's -6. So it's -4 divided by 6. So each carbon here is, the charge of each carbon is -4 divided by 6. And then on this other side here, we know that oxygen is -2, hydrogen is +1. So this, right? This oxygen here is -2. And this carbon here is +4, right? Because I have 2 oxygens giving -2, so we need to have the carbon giving +4, so the molecular is 0. Okay, so we know that 2 things are happening here. This oxygen here, this oxygen here, it's going from 0 to -2. So it's receiving 2 electrons, meaning that it's being reduced, right? Because it's becoming more negative. On the other hand, we have this carbon going from -4 to +4. So it's giving away electrons because it's becoming more positive. So it's being oxidized. Okay. So this is, so this is reduction, and this is, oops, oxidation. Okay, so that's part A. Now let's go to part B. So part B, write the balanced oxidation reaction. So our oxidation reaction, we go back here. Our oxidation reaction is the carbon going to -4,6 going to +4, okay? So, going here. So we have C6H6O going to CO2, okay? So to balance this equation, we do the 4 steps, which is first, we're gonna make sure we have the same amount of oxygen in one side, then the other side. Or first, it's the carbon, because it's all other elements other than hydrogen and oxygen. So we have 6 here. Okay. Am I recording this? Okay. Just wanted to make sure. All right, so now we know that we have 6 hydrogens in one side, and we need 6 hydrogen in the other side. But we also know that we have 1 oxygen in the left side and 12 oxygens in the other side. So we should start by adding water to equilibrate the oxygen. So if we have 12 there, and we have just 1 here, we need 11 water. Okay, so now we have 11 oxygen here plus 1, 12 in the left side. We have 12 in the right side. And the last thing that we are missing, or the second to last thing that we're missing, is the hydrogen. So we have 22 hydrogens in the left side plus 6, which give us 28. So we're going to put 28 in this side, 28 H plus. Oops. Okay, so now we have all the hydrogens that are coming in, they're going out. Last thing that we need to balance out is the charges. So we have 28 plus charges in one side and 0 in the other side. So we need to equilibrate this charge by adding electrons. So we do 28 electrons in the left side. So now the overall charge in the left side is 0. The overall charge in the right side is 0 as well. Okay, So this is the balanced oxidation reaction, which is part B. Now let's go to part C, which is the reduction reaction. And if we look back here, our reduction reaction is oxygen to CO2. So let's go back in here. So we have O2 going to CO2, and we're going to do the same thing that we did before. Wait, we have the CO2 here. Oh, you know what? These here. Sorry. These, because we're already saying that. We're saying that our carbon from the hydrocarbon molecule is being oxidized to the CO2. So our oxygen cannot be oxidized to the same molecule. It's going to be oxidized to the water molecule. So this O here, it's going to go all the way to the water here. This is the reduction. Okay. So it's where this S, right? So it's this O2 to the water, and it's this one to the CO2. Okay, ox and reduction. All right. So this goes to H2O. So we need now to balance this equation. So we have two O's in one side, so we should put 2 here. We have 4 hydrogens to the right side. We should put 4 hydrogens here. We have no charges in the right side, meaning that the overall charge in the left side needs to be equals to 0, so plus 4 electrons. All right. So now we are seeing that the equation in part C, it's consuming electrons, whereas the equation part B is producing electrons, right? So to calculate part D, which is the balanced redox equation, we need to equals the amount of electrons, because we cannot have leftover electrons, basically. So equations, part C equation, we have just 4 electrons, and part B equation, we have 28 electrons. So we need those electrons to be equal. So what we can do here is we can multiply this equation, but it's not going to be, let's see. Yeah, let's multiply this equation here by 7, both sides. So we are going to have 28H plus 28 electrons plus 7O2, and then 714 H2O. So now we can add this equation with this equation, because the electrons or the amount of energy evolved are related to each other. So whatever electrons are being produced here are going to be consumed by the other equation. Okay. And if we add these two, so we add all left side and then we add all the right side. So it's going to be 11H2O plus C6H6O plus 28H plus electrons plus 7O2. this is going to be 6 CO2 plus 28 plus 28 electrons plus 14 H2O. And we can also simplify this equation because now, you know, we have 28 H plus in one side and 28 H plus in the other side. So we can just cancel them out. We also have 28 electrons in each side. We have 7 or 11 H2O in the left side and 14 in the other side. So we can cancel 11. And here we're going to have 3 left. So now the balanced equation is going to be, let me write this on the other. Oops. So we're going to have, just make sure that I remember all the numbers. So this is 6 plus 7. So 6. Oops. Plus 702. And this is going to be, we're going to have 3 and 6 CO2 plus 3 H2O. Oops. Plus 3 H2O. All right. And just to make sure that this is right, we can count how many of each atoms going from one side to the other. We have 6 carbons in the left side and we have 6 in the right side. I have 6 hydrogens in one side, I have 6 hydrogens in the other side. We have 14 plus 1, 13 oxygens in the left side. And we have 12, 15 oxygens in the left side, and we have 12 plus 3, 15 oxygens in the right side. So that's part D, the balanced equation, redox reaction that involves both oxygen oxidation reaction and reduction reaction. And then part D, it asks write possible design modifications to increase degradation of petroleum hydrocarbons. So we want basically this equation to increase the degradation, meaning it needs to move towards your right side, right? Because you want these petroleum hydrocarbons to be degraded. What we can do is that we can purge oxygen in here, because the more oxygen you have there, the more hydrocarbons are going to be consumed. Okay, so we can do that, or we can take out CO2, because by the time you take the CO2 out or diminish the amount of CO2 that you have there, this equation is going to move towards the right to produce more CO2 in order to get in equilibrium, you know. And you can also play with the water, but water is kind of hard to play with because it's basically everywhere. But you could, for an example, heat up. If you could do that, it's usually in soil or like in a biofiltration soil. You're not going to be able to like heat up the system, you know, but it would, if you could, it would accelerate this degradation of hydrocarbons. Okay.